Alright, so today we are starting off Chapter 9. And so for Chapter 9, we're going to talk about bonding. And again, I'm hoping that everybody got a chance to watch those Lewis structures videos. So here we have our ionic compounds. And ionic compounds are weird because they don't really have a chemical bond. We call it an ionic bond, but it's not a true bond. It's really just an attraction, and we call it an electrostatic attraction. So it's the positives and the negatives being very attracted to each other. And I made this little arrow here, and the reason is there's nothing between them. There really is just open space between the cation and the anion. So they are just sticking together sort of like magnets because of those charges. But again, there's no true bond, even though we do often refer to it as an ionic bond. So they do have what we call electrostatic attraction, and I want you to know this as a vocabulary word. And that just means it's the attraction of positive and negative charges, and they do not share electrons. Another very important thing that I want you to know about our ionic compounds. They don't truly share electrons. So any questions so far about our ionic compounds? Oh, and I see Andrew's question. So yes, it is true. It does not matter the order as long as everything's in there. Different people like to write them in different orders. You'll see different methods in different textbooks. So yeah, any order is fine. All right, so other questions? All right, so next up is covalent bonding. So these are our molecules. So covalent bonds are formed by sharing electrons. And in a covalent bond, the two electrons glue or bind the atom together. So hopefully you've watched the Lewis structure videos and you've seen that hydrogen looks something like so. And this line right here represents that covalent bond, a true sharing of electrons, so a true bond. They're not just attracted to each other, they've made the commitment, they are stuck for life. Well, maybe not for life, but they are stuck together now. So any questions on the difference between the covalent and the ionic bonding, where the ionic, they're just attracted to each other, they're kind of going steady, but they haven't made a commitment yet. And then the covalent, where they actually share electrons, they're truly bonded. So now to talk a little more about Lewis structures. So what you see on the screen here, C6H6, that represents benzene. And if you've taken some biology, you may have seen a lot about that benzene molecule. If you ever go on to take biochemistry, huge important molecule. So let's talk about what benzene would look like. So in benzene, we have 6 carbons. And they're all bonded together, like so. And they all have 1 hydrogen. And this is C6H6. But you know from way back when in Chapter 1 that every carbon needs 4 bonds, and right now they don't have it. Right now they only have 3. So this is the true structure of benzene. So benzene contains 3 double bonds, and they're alternating double bonds. Sometimes we call that conjugated double bonds. And it says all of the bond lengths are identical. Well, that's kind of weird, because here it doesn't look like they're identical bonds. It looks like we have 3 single and 3 double. So now I want to draw benzene again slightly differently. So here I'm going to draw it with the skeleton structure we looked at way back earlier in Chapter 1, back when we were doing our alkenes, alkynes, and alkanes. Oops. I'm going to rotate my ring around just a little bit. There we go. All right. So this is also benzene. And way back we talked about any vertex was a carbon, and the hydrogens are just assumed to be here. So the structure that I drew right here is the same as the one above. It's just the bottom one is in skeleton format. All right, so if you've watched that Lewis structure video, you know about resonance. And so anytime you have a choice of where to put the double bonds, you want to show all those locations. So here, the double bond could have been over here. This double bond could have been here to the right, and this double bond could have been up on the top. So now I'm going to rewrite these. And I'm going to say I could have a double bond here, here, and here. And this is what we call resonance. So, oh, did I hear a question? Okay. So we have two resonance structures for benzene because there's two different locations where we could see the double bonds where they would still be alternating double bonds. But there's even a third way of doing benzene. And the third way of doing benzene, which is actually a little bit more accurate, is by putting this little circle in the middle. And if you were to read journals, this is how they usually represent benzene, with this circle, showing that the electrons don't really stay here or here. They are actually free to rotate around, and later on we're going to call that delocalized. So the electrons are delocalized if they have the ability to travel, and here they do have the ability to travel. So they're not stuck in only this location or only this one. They really travel everywhere. So when we put our benzene into one of our analytical instruments, and hopefully we'll be back on campus soon because we have a lot of great instruments in the organic lab, and one of them is the IR machine. We shoot infrared light at them, and as crazy as it sounds, we actually make these bonds bounce. And if you go on Wikipedia, you can see these great animations of how they bounce. Some of them bounce and do it this way, outwards, and some of them scissor, and they do all kinds of interesting bounces. But we have one bounce that's characteristic of a single bond, one that's characteristic of a double bond, but what we see for benzene is all of the bonds are somewhere in the middle. So here we're looking at bond lengths, and here we have a single bond that's 1.54 angstroms, and this is that angstrom we talked about way back when, I believe last class, where we said 1 angstrom is 10 to the negative 10 of a meter. And again, I'll give you that conversion. But a single bond is 1.54 angstrom. A double bond is 1.34 angstrom. And benzene is in the middle at 1.40 angstrom. So what we know is every bond in benzene really is the same, and it's somewhere between a single and a double bond. So these two structures here don't really exist. What exists is something like this, and that's why we represent this in our journals, to show that those electrons really can swing around. And in our NMR machine, we can actually tell that those electrons are moving around because in our NMR machine, we have a rotating magnet, and as we do what we call a spin flip, we can cause these electrons to travel one way, or if we flip the magnet the other way, we can cause it to go this way. So as the machine's running, it is cycling through different spin flips, and that is happening to the electrons. So first they're traveling maybe clockwise, then they can travel counterclockwise, and so on. So they really do rotate around in this circular manner. That's kind of cool. Oops. But what I wanted to emphasize here is that in benzene, again, they are all identical lengths. So we don't have single or double bonds. We truly have all about a 1.5 bond. And again, we're going to talk more about that when it comes to delocalization. But any questions about this idea that when we talk about resonance, this is just showing an example. What truly does happen is those electrons spread themselves out and they go everywhere. So questions about that idea? All right, so next up, bond length. So here what we see for a bond length is the single bond is larger than a double bond, and the double bond is, I guess I should say, longer. So the single bond is longer, the double bond is in the middle, and the triple bond is the shortest. So here we're just looking at carbon, but it applies to all of our chemical bonds. So the single is 1.54, the double is 1.34, and the triple is 1.20. So here, in terms of strength, we see the triple bond is the strongest, the double is in the middle, and the single is the weakest. So this is something you probably figured, that in terms of strength, the triple is the strongest one, but the weird thing is that the triple is the shortest. So I know normally they think big people, you must be really strong, and I'm going to tell you that's not true. So in terms of our bond length, it is the shortest one that is going to be the strongest. So I want to show you how that works. And it's a little easier in class, but I'm going to do my best with the webcam here. So think of this, get a little closer. So think of this as a rubber band. I know it's really a hair tie, but think of it as a rubber band. And I'm going to pull it out just using a normal amount of strength. I know some of you are strong enough that you could pull it all the way apart. But here it is. So this is my single bond, and I can stretch it about yay far. And it has some strength to it, but not a whole lot. If you are strong and determined, you could pull this, and you can break it. Now, I'm going to have two. With the same amount of strength, I cannot pull it as far. So because it does not stretch as far, we say that it's shorter. So a little while ago, I told you about our IR machine, and I told you that we hit these bonds with infrared light and make them bounce. So what we do is we stretch these. And in the IR, we really do call them stretches. So we stretch them, we make them bounce. And with the same amount of energy, we see the single bond stretches much further. And the double bond does not stretch as far. So when we're talking about bond length, we're also talking about these stretches. So the double bond is definitely stronger. You have to put in more energy to break it. But it's also shorter because it's not going to stretch as much. It's got more tension on here. Okay, so now I've got three, put them all together, and if I put in the same amount of strength, it doesn't stretch very far at all. And I know you might be thinking, hey, you're really wimpy. I could make that stretch, and I know you probably could. But the idea is I'm putting the same amount of effort into all of these. Single bond, with that same amount of effort, we get a larger stretch, and that's our long bond length. The double bond, same amount of effort, doesn't stretch very much. And the triple bond stretches very little. So that's why it's our triple bond that is the shortest but the strongest. So any questions on that one? I know that's weird to see over a webcam. I'm hoping that that came through okay. Could you guys see the bands okay? Okay. So in case you're like, hey, I couldn't see that, and I want a fun chemistry experiment to do at home, take some rubber bands or some hair tie, and then try it yourself. Try to make this bounce. See how easy it is for the single? It's much harder for the double, and even harder for the triple. Okay, fun chemistry experiments to do at home. All right, so down at the bottom, it says the triple bond is shorter and stronger than a double bond, which is shorter and stronger than a single bond. So again, most people are going to think, hey, triple bond, of course it's stronger. But what trips people up is that it is also shorter. So you want to think, hey, triple bond is really strong, it should be really big. But it's actually our shortest bond, and again, it's the shortest bond because it will not stretch as far when we hit it with that infrared light. So any questions on that bond length? All right, so next up it says which is predicted to have the shorter sulfur to oxygen bond. We have SO3 and SO3 2-. So here we're going to use some of our Lewis structure skills. So again, I'm hoping that you got a chance to watch that video. So let's start off with our SO3. So the first thing I'm going to do is lay out my atoms. So if you had to guess, what do you think is in the center, the sulfur or the oxygen? Excellent. So I'm seeing some sulfurs come through. Excellent. So sulfur in the middle, oxygen's around. And it doesn't particularly matter where you put your oxygens. You could have put them like so, or you could space them out a little bit, like so. The important thing is they're somewhere around that sulfur. Now we're going to count up our valence electrons. We have 1 sulfur and we have 3 oxygens. So let's grab a periodic table All right, so we're looking at sulfur and oxygen. How many valence electrons do they each have? Excellent. Excellent. So I'm seeing 6 from several of you, and that is true. We're looking at this 6 right here. Both oxygen and sulfur are members of group 6A, and therefore they have 6 valence electrons. Any questions about how we figured out the valence electron count? All right. So 6 for sulfur, and then 3 times 6 for the oxygen. So if I am correct, I believe that gives us a total of 24 valence electrons. Any questions on how we did that valence electron count? All right, so the first thing we're going to do is bond everything together, and I always start with a single bond. And each single bond is 2 electrons. So here's 2, 4, 6 electrons that I've just used. Now I go around the outside, and I'm going to give all the oxygens the electrons they need. I just used 6, so now get a thicker pen. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I have spent all of my electrons, but is sulfur satisfied? Does sulfur have 8 electrons around it? What do we think? Is sulfur going to leave the party happy? No. Excellent. So what do we do to help sulfur out? What should we do to give sulfur the 8 electrons it needs? Yes, I see a double bond coming through. Yes, exactly. So whenever you have an atom that does not have enough, we need to do a double or triple bond. In this case, a double bond. Yes. All right, so which oxygen looks very generous today? Which one do you want to take the electrons from? The top, the left, or the right? All right, so Jessica says the top, and lots of people who are fond of the top. Sorry, Top. So top was you were outvoted by the top. I apologize. I will go with yours next. So here are the electrons on the top, and they are going to come in to make a double bond. So let me rewrite this now. And I'm going to make sure I have my double bond here on the top. All right, so now I only have 4 electrons left on that top oxygen. The other ones all have those 6 free electrons, also known as 3 lone pairs. Oops. All right, so this is our new structure. Is everything satisfied? All the oxygens and the sulfur, does everything have enough electrons? What do we think? All right, let's go ahead and check it together. So if I were to look at this oxygen right here, the one that I just boxed, does that have 8 electrons? Yes. Excellent. How about this one on the bottom left? Does that have enough electrons? Excellent. How about the one on the top? Does it still have 8 electrons? Excellent. Now how about sulfur? Does it have 8 electrons? Excellent. Okay, so you were all quiet before when I asked, but now do you all agree that we have 8 electrons around all of our elements? Excellent. Okay. So now if you were asked to write this on a test or quiz, now you would want to write your resonance structures. So sometimes students say, well, how do I know that there's a resonance structure? The way you know is by looking at these bonds You did not have to do the double bond on the top. In fact, I think Tasso wanted the bottom left, if I remember. Let me scroll back over here. Bottom right. Okay. So Tasso said, no, 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 that top one doesn't look very generous today. I want it to be on the bottom right. So anytime you have the choice of where to put the double bond, you need to put it everywhere. So you need to show me that it could have been anywhere. So next up, we will use Tasso's suggestion and put it at the bottom right. So what I'm going to do is rotate this double bond around. So now I'm putting it on the bottom right. And I'm going to fill in these electrons. The top one now gets the 6 lone electrons, or say 3 lone pairs. Bottom left still has those 3 lone pairs. And the bottom right now has 2. So this could have been an alternative way of doing it. And there's one other way. And the other way, nobody gave any love to the oxygen on the left. But it could have been our double bond as well. So now I'm going to fill in the lone electrons or lone pairs, like so. All right, so again, anytime you had more than one option on where to put the double bond, you must show it in all positions, and this is what we call resonance. Technically, we do an arrow in between, but if you did not do that arrow, then I wouldn't hold it against you. Okay, questions on this right here as being the structure of our SO3? So before we move on to our other structure, I just want to remind you the true structure has those electrons everywhere. So the reason we force you to draw all 3 Lewis structures is because some of those electrons are really everywhere. Essentially, they rotate. They have free reign in this molecule. They can decide, hey, today I want to go up to the top oxygen, or tomorrow I'm going to go down to that bottom left or the bottom right. They can rotate anywhere they want. And if you're wondering, can we force them somewhere? We absolutely can. If we apply a magnet, they will follow that magnet. But if we don't apply a magnet, they can just randomly be in any of those 3 locations. They're all perfectly good, perfectly equal in terms of energy, perfectly equal locations, so they can be anywhere. And so that's why we force you to do the 3 resonance structures. So let me go ahead and note that these are resonance structures. So because we have 3 different locations a double bond could be in, that's why we have 3 resonance structures. So questions about anything that we've done here with our SO3?
For the resonance structures, my previous professor said that we could draw like a double bond on each one, but one line on the double bond would be like dotted to represent that it could change at any time. Would that be an acceptable answer too?
So let's see, it looked maybe something like...
Yeah, like that.
So this is considered a hybrid structure. If I asked you for a Lewis structure, it would need to be this one right here, yeah. But it's true that, that's the hybrid, but I would want the resonance structures, yeah. Sorry about that.
Thank you.
Mm-hmm. All right, so other questions? All right. Oops, sorry, we're not on the next problem yet. Next we have our SO3 2-, so let's go ahead and do that one next. All right, SO3 2-, so this is one of our ions. This is sulfite. So I'm going to put my sulfur in the middle, and I'm going to put oxygens all around just like last time. Now we're going to do our electron count. So 1 sulfur and 3 times our oxygen. And we said all of these have 6 valence electrons. So 6 for the sulfur and 3 times 6 for the oxygen, because we've got 3 of those. This is going to come to 24. But what do we do about that 2-? Do we add 2 or remove 2? Excellent. So I'm saying add 2. So if it is 2 negative, it's because it gained 2 negative electrons for a total of 26. So now I'm going to do the same thing I did before. I'm going to bond everything. And when I did my bonds, I used 2, 4, 6. Now I'm going to go to the oxygens. And there's 8, 10, 12, 14, 16, 18, 20, 22, and 24. Whenever you have any electrons remaining after you've gone to the outer atoms, then you bring them in. And the remaining 2 go onto the central atom. So the way I always like to do it is go to the outer atoms and then bring those extra ones, anything remaining, to that inner atom. So now let's take a look and make sure everything has enough electrons. So what about this one on the bottom right? Does that have 8 electrons? Excellent. And I realize one of my dots almost looks like a double dot there, so let me clear that up. There we go. What about the bottom left? Excellent. And our top oxygen? Excellent. And now how about sulfur? Does sulfur have enough? Excellent. So everybody is satisfied here. And now because it is a 2 negative, we put our square brackets with our charge to the outside. Okay. So this one does not have any resonance structures because there's no double bonds we need to worry about. So any questions on how we did SO3 or SO3 2 minus? All right. There we go. Okay, so our real question way before we had fun with Lewis structures was which one will have the shorter bond. So we're looking at a bond between a sulfur and an oxygen, and we want to know which one will be shorter. So here we have to remember our rules. So here I'm going to draw out single, double, and triple bond. Of these 3, which one is the shortest? The single, the double, or the triple? Excellent. Triple. So our triple bond is going to be the shortest, and our single will be the longest. Of course, the double bond then will be in the middle. Okay, any questions about that, about why the single bond is going to be the longest, where the triple bond is going to be the shortest? All right. So I'm going to start way down here. Would you agree here we have all single bonds? Excellent. So definitely single bonds. Now over here, they're not exactly single bonds. Now if you recall that triple bond really spreads itself out over everything, so I'm going to say that the sulfur-oxygen bond is 1 1/3. And we're going to talk about something called bond order in a little bit, and I'm going to show you a calculation for how to get that 1 1/3. For now, what I want you to think about is that every one of these structures has one single bond at each location, but then we have this double bond that travels between 3 locations. So the way we got the 1/3 is the traveling of this double bond between 3 locations. That's the 1/3. So again, I'm going to show you how to actually calculate that out later, but any questions so far about how in our SO3, the SO bond is 1 1/3? Okay, so if you had to make a guess between the single bond and the 1 1/3 bond, which one would be shorter? Would the single bond be shorter or the 1 1/3 bond be shorter? All right, so I'm seeing both. I'm seeing the 1 1/3 and I'm seeing the single. Anybody else want to vote? Okay, so let's go back to this right here because we're getting mixed. So here is our single bond and here's our double bond. And we know that the double bond would be shorter than the single. So let me go ahead and get that triple bond out of our way for a moment. Okay, so the single is the longest, the double bond is a little shorter, and we know the triple would be shorter than that. If we have a 1 1/3, it would go right between here. And I'm going to use the notation that Jervin was talking about. So here, it has a full single bond and part of the double bond. So this is going to be our 1 1/3 bond. So it's going to be shorter than a single. But longer than a double bond. So if the single bond is the longest and the double bond is shorter than that, a 1 1/3 is somewhere in between them. So what do we think about the 1 1/3 bond being shorter than the single bond? Any questions on that? Because I saw on the chat there was mixed feelings about whether it should be the single or the 1 1/3. Okay. All right, so it's kind of a weird concept, but like I said, I'm going to show you later on, probably next class, how we actually calculate that 1 1/3. You're welcome at any time we're doing something and it seems fuzzy and weird, please let me know. I'm happy to go into more explanation. All right, so this one is going to be shorter. So the 1 1/3 that we see in our SO3 will be shorter. Yes, so Tasso, that's a really good point. You can assume the single bond will always be longer. It's going to be the longest of all the bonds that we have. I guess the only thing I can think of is if you had a half bond order, which is kind of a weird thing. But in practical terms, yes, single bond should be the shortest because the 1/2 bond isn't really a bond at all. All right, so this single bond is longer. No. Okay. So questions on anything here? All right. So next up, we're going to start talking about electronegativity. And electronegativity is one of those kind of weird things. So when we're talking about two different atoms and we say they're in a covalent bond, we say they're sharing electrons, the truth is they rarely share them equally. So just like if you have a friend, sometimes your friend might need to borrow some money, get a ride home. They just borrow a little too much from you. So sometimes we have friends like that. And it's often that we have elements like that as well. And so sometimes we call them electron hogs. They just take a little more than their share. And that's what you're seeing here. So here you have oxygen, you have hydrogen. And you can see these electrons aren't spread out equally. Oxygen's a little bit of a piggy, and oxygen's like more to me. So you see the electrons starting to go further around that oxygen. Essentially, they're kind of a larger bubble around oxygen of electrons. What that's showing you is, this is a probability map showing that they will spend more of their time around oxygen than they will around hydrogen. And because of that, oxygen is considered partially negative and hydrogen partially positive. So this little symbol here is a delta. When we were doing change in temperature, this was our delta. It's a capital D in Greek. Now, for our delta, we have a lowercase d. So lowercase d in Greek, or those of you who like to type out your notes, if anybody does, if you have lowercase d and use symbol font on your computer, that is where you will pull up this delta. So it is a delta, which means partial. So it is a partial negative by the oxygen, because the oxygen is getting more electrons than it should. It's not truly stealing the electron from the hydrogen. It's just taking more time with it than it should. Hydrogen now becomes partially positive, and again, this is a delta, meaning a partial charge. So hydrogen is partially positive. It hasn't fully lost that electron, but oxygen is yanking on it so much, it feels almost as if it had lost that electron. So officially, electronegativity is the ability of an element to attract electrons within a covalent bond. It's the ability of that element to be like, hey, electrons, look at me, I'm so cool, come hang out with me, you don't need to be over there, come hang out with me. That's what some of our elements are doing. I know it's terrible, they're vain, but that's what's going on, and oxygen is notorious for being electronegative. All right, so electronegative element, again, takes more of its share of electrons, and therefore it becomes partially negative. Not fully negative, because it does not completely rip the electron off of its neighbor. It just spends more time with those electrons. So it's partially negative, and the other element is partially positive. Partially positive meaning that it hasn't fully lost the electrons, but it doesn't get to see them very often. All right, so down at the bottom it says the uneven sharing of electrons is called a dipole moment, and it's measured in dBs. So those dBs, that is a numerical way of comparing two bonds to see which is more polar. And often, especially when we talk about solubility, we need to know which of two substances is more polar, and that's where that measurement comes in. And again, the measurement is called a dipole moment, and the unit is the dBi. One way I like to remember this is I think of two chemical bonds, and they're sitting at Starbucks after the quarantine has been lifted, and everybody can just sit at the coffee bar. And so one chemical bond is like, dude, I'm so polar. And the other one is like, oh, please, I'm more polar than you are. And the first bond is like, oh, yeah, let's see your dipole moment. Because that is the true measure of which one is more polar. All right. So next up, indicating the polarity of our bonds. So I'm going to start off with our HF right here. And I want to take a quick look at our electronegativity table. So on tests and quizzes, I will give you the electronegativity table, and those of you who would like a hard copy of it for your very own, if we were in class, I would hand it to you, but you can print it out if you'd like. It's on our Canvas website in the handout section. There we go. All right, so here is our electronegativity table. The noble gases tend not to want any electrons, although we do know chromium and xenon can take a little bit. But it is fluorine that is famous for being the most electronegative on the periodic table at 4.0. So in the molecule we're looking at is HF. So we're going to look at fluorine being a 4.0, hydrogen being a 2.1. So these electronegativity values are a measure of how strong this element is, how well it can pull electrons towards itself. So if you could think of a chemical bond as a tug of war over those electrons, both elements want them. If you are stronger, if you are a fluorine, you are going to start pulling them towards yourself, and poor hydrogen is like, let me have some, and hydrogen is trying to get some, but fluorine is just too strong, it's pulling. So fluorine is the electron hog, the little piggy that's taking all of those electrons, and there's a couple ways we can note that. So one way is through what we call arrow notation, and so we draw an arrow where those electrons are going. So the arrow is pointing towards the fluorine. Fluorine is more electronegative at a 4.0 when hydrogen was a 2.1. So fluorine is stronger, it's taking those electrons, and we cross the back of our arrow to show that hydrogen will be partially positive as a result of being partnered up with such a piggy. There is another way to do this, and this is the way we saw on the last slide. Here we draw a normal bond, but we use our partial notation. So this is a partial negative, and here we have a partial positive. So it sort of looks like the number 8. It's just missing this piece to be an 8. So that is our symbol for partial. And again, fluorine is partially negative because it is stronger. So it's going to take more electrons. And hydrogen is partially positive because it is weaker. So it's going to lose those electrons to fluorine. So any questions here on how I chose fluorine as the element that's going to be taking too many electrons, or the two notations that I showed you here? All right, so next up, let's do HBr. So I want you to try to do HBr in both notations. So I know it's a little hard to see, so let me zoom in here. Bromine is a 2.8. Put that 2.8 right here. Hydrogen is a 2.1. And I want you to do both notations. So do the arrow notation and then the partial charge notation. All right, so I went ahead and put up that poll, so go ahead and click in if you would like more time or you're ready to go over it. All right, so it looks like a couple people want some more time, so let's go ahead and take one more minute. So you're dealing with hydrogen and bromine, 2.1 and 2.8. All right, so let's go ahead and give this a shot. So I'm going to first look at the arrow notation. So where should our arrow be pointing? Towards the bromine or the hydrogen? Excellent. So I'm seeing some bromines come through. So our arrow should definitely be pointing towards the bromine, and we cross that back end that's near the hydrogen. So any questions on this right here? All right, so let's move on to our partial charge notation. Who gets the partial negative, the bromine or the hydrogen? Who's going to be partially negative? Excellent. Because bromine is taking more than its share, it is partially negative. Because hydrogen is getting less, it's partially positive. All right, so any questions on how we did this arrow notation or the partial charge notation, or how we decided where the arrow should point, or who should get partial negative and partial positive charges? Would the arrow change if negative? What do you mean by if negative? Do you mean if it has an overall negative charge? So we still point it towards whomever is more electronegative, just to show that the bond does not have equal sharing. So we would do it exactly this way. We would find the electronegativities, and then we would just point towards whichever one's more electronegative. All right. So if you're ever at a party, someone's taken too many chips or something like that, you can always be like, dude, you're so electronegative today. Get your own chips. Bad chemistry humor. All right. Why do we cross the back of end of H? So if you were to look at it just like this right here, it looks like a positive charge, and so we cross the back to show that it's the hydrogen that'll be partially positive. So when the electrons leave and go to fluorine, hydrogen is left with a residual partial positive. And we point to the fluorine to show that that's the direction of travel. So the electrons are kind of traveling over to the fluorine. And when they do, hydrogen has that positive charge, or partial positive. So. All right, so other questions so far? Those of you going on to organic chemistry, what you're going to see is that whenever we have electrons traveling, and I'm just going to do this to Fe2+, whenever electrons travel, we do show it with an arrow, so it always points to where the electrons are going. All right, so any other questions so far? Okay, so let's go ahead and take our break and come back about 6 o'clock. All right, so, oops, sound back up. All right, so let's go ahead and get going again. So any questions on what we talked about before break? All right, so next up we're going to talk about the trends in electronegativity, and here we're using the same arrows that we had last time. So last time we met we were talking about size, and we talked about the atoms getting smaller as you go up and as you go to the right, and we talked about fluorine and our noble gases here like helium being very small, and we talked about rubidium here being real big, and we also have our other elements down here like cesium that are also very big. So what we find is electronegativity increases as we get towards these small elements, and we have less electronegativity down at the bottom. But that should make sense. So if you can remember that the atom is primarily electrons, that is what takes up the bulk of the space. If you have a small atom, it's because those electrons are being drawn into the center. And last time we talked about them being drawn into the center by an effective nuclear charge. We called the nucleus, those protons in the nucleus, the parents, and we said the power of the parents. If the parents had more power, they're bringing those electrons in closer. So now we're going to say that there is also electronegativity. How attracted is this element to the electrons? So if the element like fluorine is extremely attracted to its electrons, it's going to bring those in closer as well, and that's going to create that smaller atom. So our smaller atoms will always have greater electronegativity, whereas the larger atoms will have less electronegativity. So if you think of real big or cesium over there, they're very large atoms. They're large because they're not as attracted to their electrons. So they are not pulling those electrons in, and instead they let them flow out a ways. So the same thing that we saw for that effective nuclear charge, if we have a strong effective nuclear charge, we're also going to have a great electronegativity. And those electrons are going to stay very close to home, which is going to make for that smaller atom. And if we have a small effective nuclear charge, we're going to have a very low electronegativity, meaning these electrons aren't very attracted to their core, and they start to drift outwards, making the larger atoms. So any questions here about why this trend in electronegativity mirrors our sizes? All right, so again, small atom is a large electronegativity. Let me go ahead and write that out just so we have it. So what we see is our smaller atoms have large electronegativity. So En is our abbreviation for electronegativity. And our larger atoms have smaller electronegativity. So in terms of what we learned for noble gases, we would call this an indirect or an inverse relationship. So if you have a small atom, you have a large electronegativity. If you have a large atom, you have a small electronegativity. Okay, so questions on anything here? Okay. And anyone need this screen for a little bit longer? All right, so here's the electronegativity chart that's in your book. And I just like showing this because it shows everything in 3 dimensions. And you can see right over here, these are our elements that have the greatest electronegativity. And over here, you have your elements that have very small electronegativity. But that said, it's kind of hard to read. So on the test, I will give you this one right here, which again, it's linked in the handout section on Canvas. I just think it's a little neater and easier to read than this one, although this one, again, it has that 3 dimensions, so it kind of is a nice thing to look at. All right, so talking about our covalent bonds. So these are bonds where we have electrons shared. We essentially have 2 different types. The first one is what we're going to call pure covalent, or as we go through the chapters, we're going to be referring to it as nonpolar, and it is more common to talk about it as nonpolar. So either of those terms work. This is where your electrons are perfectly shared. So often we're going to see this where you have 2 of the same elements together. So when I'm looking at this chlorine right here, I think of 2 twins. They are fighting over their electrons, but they're equally matched, they're equally strong, so nobody can win the tug of war. Nobody can pull more electrons towards themselves. That's what we're talking about with that pure covalent or nonpolar bond. Here the electrons are shared equally. And while in a perfect world they have identical electronegativities, we allow them to have a slight difference. So they could have a difference of up to 0.4. So somewhere between 0 and 0.4. Next up we have what we've been talking about, and those are polar covalent molecules, and we often refer to them as just polar molecules. So here's where the electrons are not shared equally, and we see electron negativity difference in about 0.4 to 2. And I know 0.4 got listed on both of them, and that's because 0.4 is kind of an iffy number. So I'm never going to give you a test or quiz question and be like, hey, it's 0.4, which one is it? That would be cruel. I would never do that to you. But I want you to know in the greater scheme of the world, sometimes things are borderline, and we actually have to perform more tests to find out, is it really nonpolar or is it polar? So again, our pure covalent, they're sharing equally. As we get to our polar covalent, somebody's taking too many electrons. They're hogging the chips, they're hogging the dip. They didn't even bring it. We're all upset. We're like, hey, stop being so electronegative and let everybody else have some chips. Anyway, okay. Then it could be a situation where they're ionic. And they're not just sitting in the corner eating the chips that belong to everybody. They have taken those chips, they've walked out the door, and they've gone home with them. And everybody's like, oh my God, they stole the chips and the dip, and they're not coming back. That is when you get into the ionic situation. So chlorine is not even pretending to share with sodium anymore. Chlorine has taken the electron for itself. That is what ionic means. The electrons are not shared at all. Somebody has actually taken an electron that doesn't belong to them. Electronegativity difference of 2 to 3.3. Again, you see that 2 in both places, and that's just to let you know there are some borderline molecules, and again, we would have to test them, and I would never be so cruel as to give you one of those on a test where you had to be like, it's 2, which one do I choose? So it'll always be obviously falling into one of those 3 categories. So any questions on anything here? All right, so on the electronegativity table that is posted on our Canvas site, you're going to see the values, and underneath you're going to see this nice little table. Now on the test, you're going to get this, but you will not get this. So this is the one that I need you to know. And here I tried to modify it so you don't have repeating values. So here, pure covalent, 0 to 0.4, and I went ahead and put polar covalent, 0.5 to 1.9, and ionic, 2 or greater. But again, I'm never going to give you one of those borderline values that make you kind of scratch your chin and have to figure it out. Questions on anything here so far?
What is the polar covalent from the note like 0.4 to 1.9?
I didn't quite catch that. So why was the polar covalent?
No, because I did see that the EN difference for polar covalent is 0.4 to 2, but on the little note table you have over there, it's 0.5 to 1.9.
So I just...
Would either be okay?
Either one would be okay, yes. So I did that because people got really stressed out about that 0.4 being in both categories. And that would be one of the tricky ones you'd have to do an experiment for, but I'm never going to give you a 0.4, but that's why I did it. I modified that so nobody had to freak out about 0.4 being in both places.
Okay. Thank you.
You're welcome. All right, other questions? All right, so the greater the difference in electronegativity, the more polar the bond. So at the beginning of all of this, I told you about the chemical bonds that were sitting at Starbucks comparing how electronegative they were, and they were comparing their dipoles. So the greater the difference in electronegativity, the greater their dipole moment would be, and the more overall polar that they will be. And if they have a large enough difference, that's when they become ionic. So in other words, we could think of here's the nice even sharing. There we go, nice even sharing. Somebody's taken a little too much, someone stole it. So those are our 3 categories. So any questions on anything here? All right, so let's take a look at how we would use that table. So here we're trying to figure out if it is pure covalent, polar covalent, or ionic. And let me just make a note here, pure covalent is often called nonpolar. And moving on through the class, we will start calling it nonpolar. Polar covalent is often just called polar. And then we have our ionics. So let's start off with our chlorine. All right, so chlorine is a 3.0. So what I'm going to do is say 3.0 minus 3.0, because they're both chlorine. They both have the same electronegativity. So this is going to be 0. So this would definitely be, and I'm going to go ahead and call it nonpolar over here. So any questions on what I did there? I subtracted the 2 electronegativity values, but since they were both chlorine, they were both 3.0. All right, so next up we have HBr. So Br is 2.8. Hydrogen, 2.1. So we end up with a 0.7, and that falls into our polar category. So any questions on that one? And by the way, if you subtract them in the opposite order, just take their absolute value, so don't worry about the negatives. All Alright, so next up we're going to do rubidium and fluoride. So here is, alright, for some reason I can't write on the fluorine, but it is a 4.0 minus our rubidium. Oh, it's because this one is stuck. Alright, okay, give me just a sec. Sorry about that, every once in a while my iPad jams. There we go. Alright, so rubidium is 0.8. And if my math is correct, I believe this is 3.2. And ionic would be a 2 or greater. So this qualifies as ionic. So any questions on where we got these numbers from or how we figured out if this is polar, nonpolar, or ionic? Let's see, is it usually the second one's element? Okay, so Jervain, you can do it either way you want, but if you get a negative, just drop your negative. But you are correct that it's usually the second one that'll be more electronegative because the second one is going to be your anion. And what we find is the cations or positive ions are on the left and the anions are on the right. So yes, it is usually, it's a long way of saying it is usually the second minus the first. But if you want to do first minus the second, it's perfectly fine, just drop the negative. All right, so other questions on anything here? All right, so just taking a look at these, chlorine, I would have predicted it to be nonpolar because it's the same element. It didn't have any choice. HBr, I would have predicted that this was probably going to be polar because these are both nonmetals. And what we said way back when we were doing nomenclature is that if you have two nonmetals, it's going to be a molecule. But way back then, we also said if you have a metal and a nonmetal, it is usually going to be ionic. So I would have predicted these even if we didn't have the numbers to back them up. So any questions on anything here? All right, so next up, electron density distribution. So these are really awesome computer-generated maps. So there is a whole division of chemistry called computational chemistry. So I knew someone who got his PhD from Caltech, and he never went into a lab. He's extremely proud of it. He did everything at a computer because he did computational chemistry. And so one of the many things that computational chemists do is they come up with these probabilities. So where is it likely we find electrons? And so here we see fluorine, and it's green all the way across, all the way around. So we predict that it will have a net neutral charge. That is to say that it's going to be nonpolar. Now here for HF, we see that is more red on the right-hand side, predicting some negativity. And then here we have the blue showing some positivity. And HF is indeed a polar molecule. And then over here we see an even greater location of electrons to the right and a smaller one here to the left. So lithium fluoride is ionic, and so this model does predict that it's going to be ionic with the red on the right-hand side, and it's got more of a separation from that blue on the left-hand side. So these are our computer simulations. By the way, those of you, and I don't know if it's only made for Apple or if you can get it on Android as well, but there's a really cool program that is free. I'm not trying to sell you stuff. Let me find it. All right, so WebMO. This is all about making those models and many more. So just to show you this briefly, and then I'm going to show you this again when we get into Vesper. But let's say I wanted to make a model, and here's my carbon, here's my hydrogen. And as you can see, I didn't do a very good job with the shape, so if some of you know this is absolutely not the shape, it should be tetrahedral. I can do a cleanup, idealized, And that is now a beautiful tetrahedral in there. And you can also run calculations with these. And so you can actually do computational chemistry. You can create the models that we saw on the previous slide, but you can actually do quite a lot. Let's see if I remember how to do all these calculations. It's been a while since I used this. It does have a great way to use the calculations, but I will have to double check how to do them because it's been so long since I've done them. But you can create those cool models. You can also calculate the dipole moment. You can look at bond length. Let's see if it'll do the one. Not yet. Let's see. It is here somewhere. I will figure out how to do it, and then I will get back to you. But this is a really cool free app to play with. I know they have it for Apple. I'm not sure about Android, and it's just called WebMO. Okay. All right, so that said, let's talk about that dipole moment. So dipole moment, this letter right here, it's called a mu. It looks like a U, but it's got a funky little tail on it. So that is our symbol for the dipole moment. And the dipole moment is calculated from the charge separation and the distance between the radii. So is it a full plus and minus? Is it a partial plus and minus? That's what our Q represents. And then the R is how far apart are these? Are these really big atoms where the nuclei are really far apart? Or are they small where the nuclei are close together? And down at the bottom it says the unit of the dipole moment is D, the debye. So your book does not go into calculations, so I am not going to require you to know calculations. So just what's on this page, I want you to know and understand how we get the dipole moment. But again, I won't ask you to do calculations here. So any questions on anything there? So next up, strength of covalent bonds. So bond enthalpy, delta H bond, is the enthalpy or energy change needed when you're breaking a bond of 1 mole of a gaseous substance. So we've seen this gas before, and what I told you before is that is just how it's defined. You don't actually have to do this in gas form. But here we have a Cl2 molecule, and we are breaking it up into 2 individual chlorine. And this actually does happen quite frequently in our upper atmosphere, so you may have heard of the problems with the ozone layer. Chlorine is one of those big problems. So under the presence of ultraviolet light, this bond gets broken, and it's what we call a homolytic cleavage, where each chlorine takes 1 electron, and it makes this right here, which is a radical. And I know it's a radical because it's got an unpaired electron, and it is this little guy that is responsible for tearing up the ozone layer. So that's why sometimes people say, you know, it's bad to use chlorine bleach, or it's bad to use white paper towels because those have been bleached, because the more chlorine gas we send up there, that causes problems. But we also have other chlorine-based molecules that we send up there, and any of those chlorine-based molecules can have this situation happen where the ultraviolet light, which is very strong up in the ozone layer, it breaks up this molecule into 2 individual neutral chlorines, not chlorides, but chlorines. And that lone electron right there goes to town on the ozone molecules, and it creates a chain of radical reactions. So that's just a side note. All right. But what we're going to be talking about here is delta H bond. So if this is my chemical bond, what we want to know is how much energy does it take to snap this in half. And one thing that I will tell you is anytime you're breaking a bond, you must always put in energy. It is always endothermic, because even if this was the weakest stylus on Earth, which hopefully it's not, if I wanted to break it, I would have to put in some amount of energy. All right. So here it says D for ClCl. So there's another way to talk about this in addition to calling this delta H bond. And that is referring to it as D, which is the bond dissociation. So again, that's just another way of saying how much energy does it take to break this bond. So it's the energy necessary to break 1 mole of Cl2 into individual Cl atoms in the gas state. And here's what we were talking about just a minute ago. Bond enthalpy is always positive. You must always put energy in to break a bond. Another way of saying this is that it's always endothermic. So if you can imagine taking your pencil, your stylus, whatever it is, and breaking it, no matter how weak that stylus is or that pencil is, it will always cost you some amount of energy to do it. That is the same thing for any chemical bond. Even if it would be more stable, if the 2 elements parted ways, it still always costs energy. That is why it is always, endothermic. Okay, so here's giving the value for our Cl2, and that is 242 kilojoules per mole. So if you have 1 mole of Cl2, you're going to need 242 kilojoules if you want to break the bond of all of the molecules in there. So any questions on anything here so far? All right, so here is a table of average bond enthalpies in kilojoules per mole. And on a test, I would supply all of these for you. Keep in mind that the bond enthalpy for a single versus a double or a triple bond is going to be different. So here, these are all listed as single bonds. That's just because the rest of the table wouldn't fit. There would be a separate table for double and triple bonds. And you can see here, everything has its own bond enthalpy. And you can also tell that you can tell that they have different energies, and we can tell which one is a stronger bond by how much energy it takes to break it. So for instance, a carbon-fluorine bond is much stronger than, for instance, a carbon-nitrogen bond. And I can tell that because I got to put in more energy to break the carbon-fluorine bond than the carbon-nitrogen bond. So this is also a way for us to estimate how strong a certain chemical bond is. So any questions on anything here? All right, so here's just showing our carbon bonds. So we have the single bond here, then followed by the double, and then the triple bond. So for carbon, we have 348 for the single, 614 for the double, and 839 for the triple. And one thing that's kind of striking is that we would have expected a triple bond would be 3 times. So the question is, why not? Why isn't it 3 times as much? And so here, what we're going to be talking about in upcoming chapters, and we'll be focusing in on the carbon-carbon bond, is that this single bond is actually a stronger bond than the double and the triple. So as you're forming a double and triple bond, you are adding something that's different than what was in that single bond. What we're going to be saying, and you don't have to learn this right now because it'll be coming up later, but we're going to learn that this is a sigma bond, and that little sigma, which looks sort of like so if it was larger, that is the strongest type of chemical bond, and that is why the carbon-carbon is 348. And what we're going to find out about the double bond is it has 1 sigma and 1 of what we call a pi bond, and the pi is weaker than the sigma. So here overall, it's stronger than the single, but it's not twice the single bond because we do not have 2 sigma bonds. Once we get into the triple bond, you're going to see 1 sigma bond, which is that strong bond. Then you're going to see 2 of the pi bonds, which are the weaker bonds. So the reason that the triple bond is not 3 times the single bond is because the triple does not have 3 sigma bonds. Hey, Kristen, did you have a question? Oh, it sounds like you just maybe unmuted yourself by accident. Okay. So any questions about this so far? And I know we haven't actually talked about the sigma and pi and what they are, but any questions so far about why that triple bond is not 3 times as strong as the single bond? Okay. All right, so now back to some fun calculations. I feel like when we're in class and I'm not doing calculations, people's calculator fingers get a little antsy and you can just kind of see them like they want to be pressing buttons. All right, so this is our bond enthalpy, and so there's this funky formula up here, and I recommend not memorizing it, and instead remember that we are going to take here are bonds broken minus bonds formed. So what we'll be doing is we will add up everything on the left-hand side, then we're going to add up everything on the right-hand side, and we're going to subtract them. So now the weird thing is that we normally do final minus initial. We do products minus reactants. This is the only time in this class where we will start with the reactants, and then we're going to subtract out the product. So let me write that down here. So here is the only time again in this class where we're going to do reactants minus products. And what we're going to be doing is adding up that bond enthalpy, or we could also call it bond dissociation energy. We're going to add that up for everything on the reactant side and everything on the product side. So the first thing that we're going to have to do is take a look at what each of these look like. So to speed us along on this problem, I'm going to go ahead and do your Lewis structures, but I've reminded you a few times now, and I'm going to nag you again. Make sure you watch that Lewis structure video. So here is our CH4, and our Cl2 looks something like so, and I'll go ahead and put in those lone pairs. So those are our reactants, and on our product side, we have a carbon, 1 chlorine, and 3 hydrogens. I put the chlorine on the top, but I didn't have to. I could have put it anywhere. I'm going to go ahead and add in the lone pairs. All right, and then we have our HCl, which looks like so. Okay, so I know I went kind of fast with doing the Lewis structures there, but any questions on what I just did? Okay, I'm going to shrink these down just a little bit so they all fit together. There we go. All right. So any questions so far about what we've done? All right, so first off, I'm going to count my carbon-hydrogen bonds. So I see 1, 2, 3, 4. So I'm going to say that there's four carbon-hydrogen bonds like so. Then I'm going to say that there's 1 chlorine-chlorine bond. Oops. So any questions on how I got my counts of the bonds that we have here? All right, so let's do 4 times that carbon-hydrogen bond. And here it is right here, 413, and these are all in kilojoules per mole. So 413 kJ per mole. All right, any questions about where I got that number from? All right, so next up we have a Cl-Cl bond. And here it is. So 2 chlorines attached to each other, 242. And when we are ready, we're going to add all of that up. So any questions on how we got these values or why we said there's 4 carbon-hydrogen bonds and 1 chlorine-chlorine bond? All right, So next up on the other side, how many carbon-hydrogen bonds do we have? All right, so I'm seeing a 3. What do y'all think? Excellent. See lots of 3s come through, and 3 looks good. 1, 2, 3. All right, what other kinds of bonds do we have? All right, so I'm seeing a carbon-chlorine. We definitely have a carbon-chlorine. Let me go ahead and color that differently. There it is. All right. And I think I see a hydrogen-chlorine as well, right over here. All right, any questions on how we came up with these bonds, that we have 3 carbon hydrogens, 1 carbon chlorine, and 1 hydrogen chlorine? Okay, so let's get our numbers now. So looking just at this previous one right over here, it looks like carbon hydrogen was 413. Now we have 3 times 413 kilojoules per mole. And that next we need to get a carbon chlorine. So it looks like carbon chlorine is 328. And finally we need our hydrogen chlorine. There it is. All right, 431 kilojoules per mole for our hydrogen chlorine. All right, any questions on where we got any of these values from? All right, so what I want you to do next is you're going to add up all of those reactant values, you're going to add up all the product values, and then you will subtract them. So reactants minus products. So go ahead and take a moment and calculate out this delta H of reaction. When y'all get values, go ahead and type that into the chat box. All right, so it looks like Tasso got negative 108 and Dravin got 104. Dravin, is yours a negative or a positive? And it looks like Ali got a negative 104. Okay, and Dravin's is negative as well. So it looks like everybody's getting negative 100 and something. So go ahead and take a couple more minutes to calculate. I went ahead and put up that poll. Go ahead and click in if you'd like some more time, or are you ready to go over it? All right, so it looks like we got a couple people who want some more time, so let's take another minute or so. Okay, so let's go ahead and go over this. So I'm going to do this on the calculator here. So we got 4 times, actually let me open parentheses, and then 4 times 413 plus 242, close parentheses, minus, and I'm going to open parentheses. Now I'm going to do 3 times 413 plus 328 plus 431. And it looks like I get negative 104 as well. So our overall answer was negative 104 kilojoules per mole. And before we go, let me go ahead and put in the intermediate answers there. Just so you have them for reference, looks like we have 1894. And from that, we're going to subtract. $19.98, like so. Okay, any questions on how we got these values? Or anybody get a different answer? Okay, let me just resize the image here for a moment. There we go. Okay, so let's talk about what this value means. So once upon a time, we looked at delta H of reaction, and we calculated how much energy was either taken in or given off when the reactions become products. We did it using delta H of formation. We also did it using Hess's law. This is just one more way to find delta H for our reaction, the difference in energy between products and reactants. So based on this negative sign right here, is this an endo or an exothermic reaction? Excellent. So I see the exos rolling in. So because of the negative right here, we know this is an exothermic reaction. So when our reactants become products, for every 1 mole of reaction, we get 104 kilojoules of energy out. So this is just one more way of finding the delta H, the enthalpy of reaction, and the final value that we're getting is the same value we would have gotten from delta H of formation or from Hess's law. So any questions about what we did here or how we did it? All right, so I want to do another one with you, and this one, again, we're trying to find that delta H of reaction. We're trying to figure out the energy that is either gained or released when we take our reactants and we form products. I'll move this to another page just so we have a little more room. And here we have our Lewis structures. Now it looks like we're missing a few lone pairs here. So I'm going to just go ahead and give us some lone pairs. Just because otherwise they look a little naked. Alright, and oxygen is double bonded. Like so. Alright, so the first thing I'm going to do is look at my reactants. And I want to count up how many of each type of bond we have. So let's start off with the bond types. So I see that we have a carbon-hydrogen bond. How many carbon-hydrogen bonds do we have? So see 6 has come in. Excellent. So we have 1, 2, 3, 4, 5, 6, and this is for the reactant side only. So I see 6 CH bonds on the reactant side. So any questions on how we determine there's 6 CH bonds on that reactant side? All right, what other bond types do we have on the reactant side? Other than carbon-hydrogen, what other types of bonds do we have? All right, so I'm seeing a carbon-carbon, excellent. So it's hidden right in the middle. Oops. But does everyone agree that there's a carbon-carbon hidden inside of there? We got one, oops, get back to blue. We have one carbon-carbon bond, like so. All right, what else do we have there? Yes, we have an oxygen-oxygen double bond. And we have a 7/2 coefficient in front of it, so we're going to have to keep that 7/2 coefficient. So any questions on anything so far here? All right. So let's go ahead and find our carbon-hydrogen. And here it is, 413, just like before. Next, we're going to need our carbon-carbon. By the way, this is the same image as before, it's shrunk down a little so we could get the double and triple bonds on there. And I know the resolution isn't as good, I apologize. All right, so carbon-carbon and 348. Like so. All right, now we need the oxygen-oxygen double bond. And it's down here in the double bonds. So sometimes we have a molecule that's so common. Here we just list it the way it is. And so this is our O2, but it is listed under multiple bonds because it is truly an oxygen-oxygen double bond like so. All right, so I apologize, we had some technical problems there, but let's go ahead and take a look at our products. And first off, I want to look at our carbon dioxide. So carbon dioxide, CO2, based on our balanced chemical equation, we have 2 of them. So what that means is we have 2 of that CO2 molecule. So let me go ahead and draw out one more of these. Now in terms of chemical bonds, it doesn't matter whether it's OC or CO. I'm going to go ahead and write it as carbon double bond oxygen, but again it could have been oxygen double bond carbon. The idea is it's a double bond and on one side there's an oxygen, the other side there's a carbon. So again, I'll just go ahead and note it as carbon oxygen double bond, but if you prefer oxygen carbon, perfectly fine. So here I'm going to count up 1, 2, 3, 4. So we have a total of 4 of these carbon oxygen double bonds. So when in doubt, you can always draw out those molecules and then count up the number of bonds. But there is another way to do this, so let me show you the other way. So here is our carbon double bond oxygen, our CO2, and based on our balanced equation, we're told that we have 2 of them. So first of all, I'm going to look inside the molecule, and I see 2 bonds that connect carbon and oxygen. So here I'm saying 2 C double bond oxygen chemical bonds, but then there was another 2 right over here. So this is 2 times 2 carbon oxygen double bonds for a grand total of 4. I'm going to use an arrow just so we don't confuse our double bond and our equal sign. That is 4 carbon oxygen double bonds. So whether you want to do it here by the multiplication or here by actually counting up the bonds, either way you come to 4 carbon oxygen double bonds. So right over here, I'm going to say 4 carbon oxygen double bonds. Next up, we're looking at the water molecule. And here we have those same options. If we want to, we can write out 3 water molecules. And now we can count up these bonds. They're all OH bonds, even though some of them are hydrogen to oxygen, some of them are oxygen to hydrogen. I will write them as OH, but again, if you prefer, HO works perfectly well. All right, to count these up, 1, 2, 3, 4, 5, and 6. So we have a total of 6 oxygen-hydrogen bonds. But of course, we can use our multiplication method. And in practice, most students prefer the multiplication method. So let's take a look at that. I'm going to move this out of our way. All right, so we have 3 of the water molecules. And we know every water has 2 of these oxygen-hydrogen bonds. And we have a coefficient of 3 in front of them. So I'm going to say 3 times 2 OH bonds, and I'll use an arrow instead of an equal sign just so we don't get confused with chemical bonds. So 3 times 2, trying to avoid those equal signs, sorry. Let's just say 3 times 2 are 6 OH bonds like so. All right, so either way you want to look at it as 3 times 2 OH bonds, or if you want to think of it as 6 total bonds in there, either way you're going to have 6 OH bonds. All right, so next up on the right-hand side here, let's get our value. So we have 4 times our carbon-oxygen double bond. Since it is a double bond, we're looking at the multiple bond section. And here's that carbon-oxygen double bond. Remember, we never want to just multiply the single bond by 2 because the double bond consists of 2 different types of bonds. So a CO double bond is 799 kilojoules. And I should say 799 kilojoules per mole. Now we're going to do 6 times our OH bond. And the OH bond is 463 kilojoules per mole. All right, so from here, we're going to have another little technical jolt, and then we're going to join the rest of the class. I apologize for the technical difficulties. All right, so let's start over here with your reactants. So what value did you get just for the reactants? Anybody brave and proud of their reactant value? All right, so it looks like 4,558.5. Everybody else get a similar value if you did your reactant separately? I guessing that a lot of you just did it all together, probably? Okay. That's okay. We'll go ahead and do the products together. All right. So for the products, 6 times, or I'm sorry, not 6 times, 4 times 799 plus 6 times 463. And here it looks like I'm getting 5,974 kilojoules per mole. And then we have 4,558.5 minus that answer. All right, and this looks like the value that everybody's been getting. So if we subtract these two, we get our delta H of reaction, a negative 1,415, and with sig figs, I'm going to call that 1,416 kilojoules per mole, like so. Excellent. All right, so what this is saying is we have an exothermic reaction, and every time we run this reaction, we're going to get negative 1,416 kilojoules produced. All right, any questions on how we did this one or this previous one over here? So I definitely want you to be able to use these bond enthalpies. You can call them delta H bond or bond dissociation. Either way, I want you to be able to use those to find the delta H of reaction overall. All right, so next time we're going to start looking at ionic compounds. So ionic compounds is, I want to say, big and beautiful calculation. Most students don't always add the beautiful part, but it's a beautiful calculation, but it's also a large calculation. So just be ready for that. We're going to start off next class with that big calculation. We're going to find out what we call the lattice energy. So we'll be looking at a crystal lattice, and a crystal lattice is an ionic compound. So the idea of the lattice energy is how much energy would you need to break this up into gaseous ions. So it's usually a very, very large amount of energy. So either if we are breaking this up or we putting it together, it always involves a large energy exchange. And one of the reasons, way back when we talked about our net ionic equations, and we said there's got to be a reason that these reactions happen. And I told you the formation of a solid is a very good reason for it to happen. I told you that if we can form a solid, a liquid, a gas, a weak acid, or a weak base, your reaction is going to happen. So solids are extremely favorable, and the reason is that they give off a lot of energy when they form, and if you were to try to break it up, not by dissolving it in water, but just ripping it apart, you would have to put in an extraordinary amount of energy. For instance, if you wanted to melt sodium chloride, melt table salt, you would have to get it up over 1,000 degrees Celsius. So interestingly, if you looked in our lab, in the back corner of the lab, and we never really got a chance to use it, that there was this Fisher burner that was attached to an apparatus that would have kicked out hot air for our molar mass lab. But that Fisher burner is one of the few burners that can go over 1,000 degrees. So if you put sodium chloride, you put rock salt over your Bunsen burners that you have at your own tables, you could not get it to melt. It needs so much energy. You need a Fisher burner to get it over 1,000 degrees Celsius. So just to show you that, before we go, I want to show you a quick video of this.